We all use lithium-ion batteries in our day-to-day lives, most commonly for things like powering mobile phones and laptop computers. But in the future, we're going to use them for a much greater range of different things. For example, we're already seeing lithium-ion battery-powered cars on the streets of London. However, as we move to more and more demanding applications, it's crucial that we understand how these batteries can operate safely. We've seen recently a number of high-profile incidents reported in the press associated with lithium-ion battery failure.
Quite a lot of heat is generated within these cells during failure, and the failure could spread to neighbouring cells.
Thankfully, these events are extremely rare, so what we're trying to do here is understand, using these experiments, exactly how the failure begins and what the consequences of that failure are, and hopefully by understanding this mechanism of failure, we can begin to mitigate against the likelihood of these failures occurring.
Up until now, generally X-ray imaging was used for looking at batteries before and after failure. But because we had the ability to look at during failure, we decided to combine thermal imaging and high-frequency X-ray imaging to look at both what happens on the outside and what happens on the inside of these cells during thermal runaway. Thermal runaway is a process in which, when at a critical temperature, the materials inside these batteries start to break down exothermically, so they generate a lot of heat while they break down. And when heat cannot escape as fast as it's being generated, this is a runaway reaction that cannot be stopped. We tried to simulate a range of abuse conditions, so from moderate temperatures up to try to simulate a fire. So in this case, the batteries were subject to about between 250 and 300 degrees Celsius. And so by looking at these cells during failure, we could potentially improve the safety of them, which when scaled up to thousands inside a module, can significantly improve the overall safety of the system.
So the key finding from this study is using X-ray radiation to study in situ how these batteries fail. And by identifying the failure mechanisms within cells like these, we can propose mechanisms to design safer battery packs for a range of different applications, including automotive powertrains.